So it is a pleasure to welcome Eduardo Dueñez, who will talk about complexity of deep computations via topology of function spaces.
Yes. I want to thank the organizers, particularly Mrinal, for this new initiative of the Institute that he is starting and for organizing these sessions. And thank you, Karen, for being here. It's so early in the morning. Anyway, I'm sort of like a little bit of an outsider slash periphery person to dynamics. And so I'm going to talk about some joint work joined with my colleague Jose Jovino at San Antonio, UT San Antonio, and two graduate students, Tonatiuh Matthews Widerhold and Luciano Salvetti, and their advisor, topologist Frank Toll at Toronto. Anyway, so right. So it is about using it. This is more of a has more topology than dynamics, this talk, but I mean so there's a little bit of both. And since topology is in the title of the session, I think um I'll be happy talking about this. So the first thing is it is about the notion which is very relevant nowadays in terms of everything having to do with artificial intelligence, neural networks, and everything having to do with real values computing, to put these things in some sort of framework and talk about the complexity of computations. But so first, sort of like a tongue-in-cheek um, look at Stone-Weierstrass, right? Is well, um, so the idea that a computation, what we call a computation in sort of like terms of real numbers, depends on the ability to evaluate some continuous operations that are basic ones, but only within a tolerance, right? So this is the type of thing that a floating point arithmetic library does, which is that the silly thing is that we use digital exact algorithms to emulate software slash topological computations with real numbers, right? But one of the key starting points for what we do is the idea that it doesn't matter what floating point library of arithmetic you're using, it will only ever work on a specific compact subset of the reals and only up to a specified degree of accuracy, right? So one way to look at Stone-Weierstrass sort of computationally is that if, let's say, you have a map on a finite dimensional vector space, this we're gonna soften later. Finite dimensionality is gonna be softened, and the fact that V is a vector space will also be softened. Yeah, but the point is that if you only can never use algorithms to compute, specific algorithm is bound to a specific compact subset, a degree of precision. And notice that I wrote that V is a vector space, right? So it also applies implicitly on the coordinatization of the vector space. So of course, in applied mathematics and engineering, the vector space is always Rn, it's always finite dimensional, and it's always explicitly coordinatized. But a lot is gained and sort of like the starting point for our approach to soften these things. So take a critical look. Okay, so as I said, the key so Stone-Weierstrass can be seen as sort of a computational the existence, the possibility to implement in floating point arithmetic a real valued function, right? The evaluation of a real valued function on let's say on a subset of a vector space. So there's, as I said, the precision, the choice of a compactum, and the coordination are all important, right? Now, so we start softening, so sort of like moving, softening some of these conditions. So for instance, the first one is that many times we don't really want to evaluate a function on an entire vector space, but only in some subsets. For instance, logarithms are not really defined on all of the real line, but only, positive reals. So of course you want to be able to compute such functions. All right. So on the other hand, this of course jives very well with Philip's talk and the talk about separability and Polish spaces, is that the finite dimensionality is in a sense a red herring. I'm only gonna be talking about some of the reasons, but let me just say that ultimately, um, a lot of what happens in modern computing, especially in machine learning, is randomized computing. And the moment you are dealing with probability measures, you're dealing with spaces. How do you parameterize probability measures? The spaces are very much infinite dimensional, even if in principle you may only be interested in a finite number, the study of a number, a specific one, or a finite number of computations. But anyway, so even though an algorithm can only ever use finitely many real valued features once you fix your precision, as the precision goes to zero, the number of real valued quantities in the algorithm may grow indefinitely. So in a sense, the algorithm as an ideal, the collection of algorithms of stricter algorithms as epsilon shrinks to zero may eventually depend on countably many real valued sort of like features of the states that you're looking at, right? And in fact, some real features in many cases might be coordinates, but not necessarily so. So for instance, it is a very natural feature of a norm vector space is the value of the norm. So it is a real quantity that may be sort of like a computational primitive, not something you are computing, but an ingredient of the algorithm that is used to compute something else. So this kind of like brings the idea that it's generalized coordinates that are relevant. So this is like a prelude to the idea of purely relational real value structures, which it's really a way of embedding your state space in a product of lines. So the idea of these purely relational value structures is sort of like, this is not a particularly deep definition at all. In fact, you could get at it in many different ways, but this is directly inspired by notions from real valued structures, real valued logic. So what we call a computation state structure, right, is essentially something which has a natural and specific embedding into a product of real lines. The embedding is topological in the sense that the topology on the set of states, which again as I said, essentially you can think of that as a subspace of a Euclidean space. And in this case, we're taking a countable product. I mean, finite being a special case of this, really. Uncountable being harder, countable being the sweet spot for many applications and analysis, right? And all that you have is that this topology is initial by some continuous functions. In other words, essentially, what you have is in any material sense, simply a subset of Rn. It doesn't even have to be closed or possess any other nice topological properties. But the case when this is a closed subset of Rn in the topology of pointwise convergence is pretty important. And it's sort of like the setting in which the methods of model theory apply, really. Just if you do this embedding, then what we're calling a predicate is simply a coordinate. So that's pretty simple so far. This is just a way to talk about, so what we're saying is to talk about the states of a computation, just give it coordinates in an explicit way. The key here is that the coordinates are explicit, fixed beforehand, once and for all. So this is a structural perspective where these are literally structural predicates. This is what the model theory opens the door to model theory. All right. So as I said, the state structure always carries a topology of coordinate-wise convergence, of entry-wise convergence, right? I'm not even going to, I mean, I assume you all know what that means. But the point, one of the advantages of the model theoretical perspective is that you shed light on theories, which is the systematic study of relationships between predicate values, how independent or correlated or dependent they are between it with respect to each other. So that's gonna come into play in the main results of this talk. And then also in parallel, the possibility to explicitly define specific real functions. So if there's a real function you want to compute, one way to think about it is in terms of the existence of an algorithm, but the model theoretic way to capture that is in the sense, and then is the concept of definability in the sense of, let's say, a specific logic, let's say, first order real valued logic, which is like an analog of first order standard logic, but where the quantities that you're studying are not binary predicates, true, false, but real valued predicates. So there's a very natural analog of what we call the standard first order logic, but when you're dealing with real valued predicates. And in that notion, and in that sense, definability is essentially what captures the notion of algorithm we were talking about before. So it's on a compact, you can approximate arbitrarily well with continuous functions of finitely many predicates at a time. I'm not gonna say more about that. I'm gonna leave it at that level. But let me sort of like connect this to the perennially hot contemporary topic of neural networks. In fact, the discussions that led to the paper that started this program, which is not the one I'm focusing on today, but an earlier one with just a team of UTSA people, had to do with what is referred in the neural networks literature as deep equilibria. And let me just sort of like try to explain what that means by means of a picture. So you have a state that is captured in terms of some real valued quantities. Each of these is a real valued quantity. It's a predicate, so to speak, right? And you apply a certain transformation that maps this initial state into what is known as a hidden state, which is also characterized in terms of real valued quantities, which are obtained in some effective continuous way from the coordinates of from the predicates of the input, right? So you get other real valued quantities, and then in order, I mean, in general, a network keeps doing this indefinitely, well, a finite number of times until you get to the values in a specific output layer where you read the real values that you obtain after so many steps followed in so specific ways. But in order to talk about deep equilibria, this has to be discussed iteratively. So you keep applying the exact same function. So this is really nothing but an action of the semigroup of naturals. It's a system, right? Of iterative applications of the same. And the people in neural networks ask, what is the deep state of a computation, but which they mean what is the values of the features in the hidden layers that you're obtaining after continuing the computation until it stabilizes. At least that's the way they think about it. Of course, we know dynamical systems don't have to converge, orbits don't have to converge to a fixed point, of course. So it's much more complicated than that. Um, um, but so actually, I'm going to start just a basic theorem, basic result could be an idea of what's happening. But this gives to the idea of computational computation structures, which are the ones that result from applying an algorithm iteratively and indefinitely, so to speak. And to this effect, I'm just going to state like a theorem that is really a corollary of Ellis-Namakura, except with the condition of compactness a little bit relaxed, right? Because we're not necessarily in a compact setting, but only working on one compactum at a time in something that may be non-compact. But for instance, a deep equilibrium is an ultra computation that has become idempotent. So you realize it, you carry it out, and then you carry it out again, and it's the same as having only carried it once. So in a sense, it's a computation that in the pointwise convergence topology is it's a fixed point under the iterations, right? The point, of course, being that once you go to the limit of continuous transformations, you do not necessarily get a continuous one. So, well, anyway, so let me that a very simple and familiar example is the Newton-Raphson dynamics and the Newton fractals, where by iteration of the Newton map that gives the successive steps of Newton's method, at each step the map is continuous on the Riemann sphere, but after indefinitely many steps, you're hoping to converge to a fixed point, but even when the map converges to a fixed point, like it is going to be discontinuous, depending on what route you're converging to. And in general, the situation is even more complicated because you may not be converging to a fixed point, but to an orbit. So here we have an example of, just for a picture of the zq minus 2z plus 2. And let me switch to this picture here, where as you iterate 1, 2, 3, blah, 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 99, 100, and 101. So you have convergence to one of the roots of the cubic, another of the roots of the cubic, another of the roots of the cubic with red. But then you see this alternation between cyan and magenta, where you go into a 2-point orbit 0, 1, 0, 1, 0, 0, 1, 0, 1. Okay? And of course, what is left is the Julia set, which is the neutral fractal proper. So again, this is an illustration of that when you do the iteration of dynamics, you may certainly leave continuous functions, and those continuous functions might actually be pretty bad. In the neighborhood of a point of the Julia set, the limit is not even a bare one function. So let me go there. Of course, if you take any initial point and you iterate, you're going to converge somewhere along a subsequence. But the problem is that you may not be able and will not be able to do that simultaneously for all the points in a neighborhood of a point in the Julia set, right? So the limit dynamics of Newton-Raphson are not bare one. So let me remind you that bare one functions are the ones that are obtained as point ones limits of continuous ones. So for instance, the Thomae's function, which is like 1 over q for rationals and 0 otherwise, right? 1 over the denominator for rationals and 0 otherwise, is bare one. And here's like a continuous approximation to it. But if you do the Dirichlet function, which is a characteristic function of the rationals, which is basically just like 0 and a 1, that's bare 2, that's not bare 1. So that's way worse. Okay. So the picture here in the neighborhood of the Julia sets, you have something that is bare 2, not bare 1. So it's actually pretty bad. Now the main result connecting bare one dynamics. So either real computations that are obtained as pointwise limits, or dynamic computations, transformations of the space that are obtained as pointwise limits. When you start with a set of continuous functions, either you get, well, here there's no, either you get a set of transformations where all of the ones you obtain as limits are actually bare one. But and when I say limits, I mean ultra limits, sort of like in a pointwise way. So a priori, they're not pointwise, they're not sequential limits, right? But only points of accumulation in the topology of pointwise convergence. And the ability to actually approximate them at every single point as a sequential limit is the property of bare one being bare one. And that happens for a collection of continuous functions. You only get bare ones as accumulation points precisely when the set of functions has the no independence property, which I don't want to go into the technical details. I'm not going to say really very much about it. But the point of the no independence property is that it captures the finiteness of the Vapnis-Chervonenkis VC of the dimension, which measures sort of the information. So the complexity of the set of functions that you have, and it also speaks to a limited ability of the functions to be used as classifiers of sets of arbitrarily large size. So bare one is essentially the other side of the coin of the no independence property, which is the other side of the coin of there's a coin with three sides of the finiteness of the VC dimension. Well, so now, so I'm just the point has been to sort of like give you an idea of how we're using this point of view based informal by model theory and topology to classify the complexity of computations and ultra computations, and in particular try to convince you that bare one is the good ones and anything beyond bare one is just really pretty bad. And I'm just gonna invite you to look at our preprints, but essentially building on the results of Todorchevich that classify the bare one case has gradations of increasingly more wild behavior, even within this relatively tame class of bare one / NIP. You have subclasses. So these Rosenthal compacta is a compact subsets of bare one functions. And there is a classification that comes basically from the results of Todorchevich, depending as to whether the space that you get of the bare one space that you get when you take the closure of this, that the continuous transformation is started with, whether it's heterogeneously separable, non-heterogeneously separable, or metrizable. So there's increasing or increasing ways of complexity within the tame class. So I'll just finish that. There is actually a much more recent result that goes to 7 classes. This is Argyros, Zodos, and Kanellopoulos, but I'm not going to talk about that. You can look at the paper. And the essential takeaway is that NIP is a dividing line between computations that may not be continuous, but still have some hope of being approximated by algorithms, and the wild ones that are bare 2 and beyond. So with that, I will stop and thank you for your attention.
Well, thank you very much.
And yes.